Your database is lying to you. It looks like data is retrieved instantly, but underneath, massive indexing systems are constantly reorganizing terabytes of information just to answer a single query fast enough. And today, we're breaking down exactly how that works.
Welcome to the Explainer. You know, when we click Save on a profile update or fetch our purchase history on an app, we kind of just assume the database is a simple filing cabinet. You put a file in, you take a file out. Simple, right? But think about it. If your system actually had to scan an entire modern hard drive from start to finish just to find one specific user record, your application would literally grind to an absolute halt. The idea that saving and retrieving data is just this simple magical process is a complete illusion. To give us that lightning-fast performance we all just expect nowadays, databases are actually performing this elaborate non-stop dance of sorting, splitting, and merging, entirely behind the scenes.
Section 1. The illusion of instant data. Let's start with the fundamental challenge here, which is finding data on a disk without reading every single byte. To solve this lookup problem, engineers use an index. An index is basically an additional data structure derived from your primary data. It's exactly like the index at the back of a massive textbook. It acts as a signpost, telling the system exactly where to jump to. But here is the absolute catch. While a well-chosen index will drastically speed up your read queries, every single index you add inherently slows down your writes. Why is that? Because every time you write new data, you don't just write the data, you also have to update the index. So you're always trading write speed for read speed.
To really picture this, imagine the absolute simplest database possible. One that just takes every new piece of data and appends it to the very end of a log file on the disk. Appending is practically the fastest way you can write data, period. Now, to find that data again quickly, without scanning the whole log, we just keep a basic hash map right in the computer's fast memory, or RAM. This hash map maps every single key, like a user ID, to the exact byte offset in the log file where that data lives. So a read request comes in, the database checks the in-memory hash map, jumps straight to that exact byte on the disk, and grabs the data instantly. It is incredibly fast. But keeping every single key in your RAM just doesn't scale when you start hitting millions or billions of records. You'll simply run out of memory.
Section 2. Appending logs and LSM-Trees.
So how do we solve this scale problem while keeping those blazing fast write speeds? Well, we use a kind of counterintuitive approach. What if we organize the chaos of incoming data before it ever even touched the hard drive? That is the magic behind log-structured merge trees, or LSM trees. When a write comes in, it's first added to an in-memory balanced tree, which we usually call a memtable. The cool thing is it gets instantly sorted by its key right there in memory. Once that memtable gets a bit full, maybe a few megabytes, the database flushes it out to the disk as a perfectly sorted file called a sorted string table, or STable. Because the data is already sorted in memory, writing it out to disk is a super fast sequential operation. But as you can probably guess, over time you're going to end up with hundreds and hundreds of these separate STable files scattered around.
And that's exactly why the database runs a continuous background process called compaction and merging. It cleans up this mess without ever interrupting the live running system. Since every single individual SS table is already perfectly sorted by its key, the database can just read them side by side. It's literally the famous merge sort algorithm in action. The system compares the top keys from the files, writes the most recent version of the data to a brand new file, and permanently trashes any older, overwritten, or deleted values. So the system is just constantly organizing and cleaning itself up in the background.
But wait, how does this actually fix our memory problem from earlier? Well, because we know the data on the disk is guaranteed to be perfectly sorted, we no longer need to keep every single key in our in-memory hash map. Instead, we can use what's called a sparse index. We might only keep one key in memory for every few kilobytes of data. For example, if we're searching for the word handiwork, our sparse index might just tell us that it's located somewhere between the words handbag and handsome. The database jumps to the handbag offset on the disk and just scans forward a tiny bit until it hits handiwork. This simple trick saves massive amounts of RAM, making systems like Cassandra and LevelDB capable of handling truly astronomical amounts of data.
Section 3. The ubiquitous BTree. Now, while LSM trees are absolute powerhouses for heavy write loads, we have another structure that prioritizes lightning-fast, highly consistent reads, the ubiquitous BTree. Used in nearly every major relational database out there, BTrees take a completely different architectural philosophy. Instead of appending data to variable-sized logs, BTrees break the database down into fixed-sized blocks, or pages, which are traditionally 4 kilobytes each. This is by design because it perfectly matches the architecture of the underlying hard drive. Finding a key means starting at a single root page and following references down the tree.
At each step, you narrow the range until you hit the exact leaf page containing your data. It's a highly structured, incredibly predictable search.
But obviously, data isn't static. We are constantly inserting new records. So what happens when one of those 4 kilobyte pages fills up completely? The BTree handles this brilliantly by simply splitting that full page into 2 half-full pages. It then updates the parent page above it to point to these new boundaries. This self-balancing property is absolutely phenomenal. It guarantees that a BTree containing millions or even billions of keys always remains just 3 or 4 levels deep, meaning finding literally any piece of data requires following no more than 4-page references. That gives you incredibly stable, ridiculously fast read performance.
So it really all boils down to understanding the trade-offs between these two titans of transaction processing. On one hand, you have the log-structured school with LSM-Trees. They append data, they use variable-sized segments, and they generally win big on write throughput and disk compression. On the other hand, you have the update-in-place school with BTrees. They overwrite data on fixed-sized pages and typically offer much faster, more predictable reads, and because every key exists in exactly one specific place in a BTree, they also provide fantastic support for strong transactional locks, which is exactly why banks and financial systems absolutely love them.
Section 4. Transactions versus Analytics.
Up to this point, we've basically been talking about looking up an individual user profile or updating a single shopping cart. But what happens when we pivot and we need to start analyzing millions of records all at once? Well, we enter a tale of 2 workloads. On one side is online transaction processing, or OLTP. This is your live application. It's fetching single records instantly, processing low-latency user inputs, and dealing with the most current state of the data. On the completely opposite side is online analytic processing, or OLAP. This is your internal business analysts trying to figure out company-wide trends over the last 5 years. They aren't looking up one user. They are aggregating terabytes or even petabytes of historical event data. These read patterns are just so fundamentally different that trying to do both on the exact same system is a complete recipe for disaster.
Section 5. Building the data warehouse. So, how do massive enterprises actually run these incredibly heavy analytics queries without immediately crashing their live apps? They use a scale-out solution. Companies protect their critical, user-facing databases by physically moving the analytics workload somewhere else. They deploy an extract, transform, and load pipeline, commonly known as ETL. This pipeline continuously extracts data from all over the place, like the e-commerce database, the inventory database, the routing database. It cleans it all up, transforms it into an analysis-friendly format, and then loads it into a massive central repository.
That central repository is what we call the data warehouse. It's a completely separate database, highly optimized entirely for analysts. You simply cannot run a query that scans 10 years of sales data on your live OLTP database without risking severe slowdowns for actual end users who are just trying to check out their shopping carts. The data warehouse solves this problem by giving analysts a safe, read-only environment to explore the enterprise's entire history, completely isolated from live operations.
Inside this warehouse, the data is usually structured in what we call a star schema. You'll typically find a gigantic central fact table, which logs every single event that ever happens. Every single row is an event. It then links out to much smaller dimension tables that describe the event in detail, like who bought it, what they bought, where, and when. Visually, the relationships look exactly like a star. But scanning a fact table that has potentially trillions of rows presents a massive physical hardware bottleneck, namely disk bandwidth.
Section 6. Column-oriented storage power.
So, here is the final mechanical trick engineers use to make massive data warehouse queries structurally possible. To scan trillions of rows incredibly fast, data warehouses abandon traditional row-oriented storage entirely and instead use column-oriented storage. Instead of storing an entire row's data together on the disk, they take all the values from a single column and store them together. So if an analyst runs a query that's just checking the price and date columns, the database only loads those 2 specific column files from the hard drive, completely ignoring the hundreds of other columns. This drastically reduces the disk bandwidth bottleneck. Plus, because a column file contains millions of similar data types, like a column of just dates or just country codes, it enables massive data compression. And fascinatingly, to handle writes to these heavily compressed columns, modern data warehouses often rely right back on those LSM trees we discussed earlier, batching updates in memory before merging them down to disk.
From simple hash maps and brilliant LSM tree compactions to beautifully balanced BTrees and heavily compressed column stores, the sheer mechanical scale of storing and retrieving data is just breathtaking. As databases specialize further into massive analytical columns and hyper-fast transactional trees, it really makes you wonder, what invisible, incredibly complex structures are working overtime right now, sorting, splitting, and merging terabytes of data just to load your next app notification? Definitely think about that the next time you hit refresh. Thanks so much for joining me on this explainer, and keep exploring.